Okay, so welcome to a Forensic Geophysics lecture. We're looking at using geophysical methods to find not always buried objects, things in water, and other items of interest. So this is a case I worked on a few years ago up in Blackpool, looking for an unfortunate individual. You can see we've surveyed off an area. We've actually radar profiles over here, and we've put flags where we think interesting objects might be located. In the end, it was a pipe, not a person, but the police team were happy that there was actually objects there that in the survey area they specified. So by the end of this lecture, you should be able to look at how those sort of main geophysical surveys fit within overall frameworks of search, show you the sort of different techniques and their equipment configurations, show you some relevant case studies, and so you should be able to choose a technique relevant for a particular thing you're trying to find. So all sorts of things you can look for geophysical targets. So geophysics is sort of physical properties of the ground that you measure, literally. So things like I've just talked about graves. Could be single or mass graves. They could be recent or old. They could be shallow or deep. So there's obviously different scenarios. Talked about conceptual site models as well, if you know what you're looking for. Could be other things as well. I think other things get buried, sort of money stashes, stolen goods, things like that. Could be more unusually vehicles that get dumped and buried. Could be things such as where we disturb ground, if some primary and secondary deposition sites, for example, trying to pick up the first one if it's been moved, or even people living on a certain area. So again, all those sort of things are of interest, but obviously graves are the highest profiles. That's the one I've been talking to you about. Okay. So you've got a sort of a statement. The police have come to you and said, "Oh, we think someone's been, say for example, being buried." Obviously, surface ones are easy. Certainly in the UK, we're a relatively populated country, and it's small. The nation of dog walkers, you can generally find people. So very hard to find on a remote site. So buried ones are the ones you'd be looking for. And if you can't walk over and find it, or dog teams can't find them, then what else should you use? So as we mentioned, most cases are solved conventionally by police intelligence, witness statements, confessions, intelligence-led observations, that side of things. However, rarely it may not work. People might not be a crime of passion, or people haven't got their phones with them. They can triangulate where they've been. Could be something else. And Ian Brady at the Moors murders in the 1960s is a good example of that. So where a massive search area, small person just trying to find Keith Bennett is the only one they haven't found, one of his victims. So how would you go about looking? So we come in. So dogs, I've mentioned. Thermal imaging actually is quite useful, especially if it's a recent burial, or even a person that's on the surface. You can still pick that up. We'll talk about that later. You can walk over, lumps and bumps. What's next? So what is forensic geophysics? It's not this guy. He doesn't seem particularly interested. What we're trying to do is we're measuring things, sort of application of methods to look for things legally. And it's not all just on land, it's underwater as well. Only 10% of people statistically get buried, 30% get in water, and 60% of the rest are in structure. So it's not all just buried in the woods, as you might imagine. And hopefully, forensic geophysics, we don't just stay off the grounds. We search an area and say, right, these areas look of interest. So then other people then will do follow-up work with that, perhaps digging up the sites we specify. But we sort of emphasise that it could be other objects as well, or other things causing the geophysical response, which obviously isn't ideal, but that's the way the thing works. So it's been going for sort of 20-30 years or so, sort of back from the 1990s really. It's a bit more mainstream and dominated by ground penetrating radar, or GPR for short. So the unfortunate individuals on the bottom left, they're sort of mass graves in Iraq. You actually pick those up from remote sensing methods, or they were tracked there, or in vehicles. We're more looking at the isolated buried individuals, such as this unfortunate in Eastern Europe in Bosnian civil war victim there. So they're a bit more, that's more what you're looking for. And of course, it depends on the length of the time that the person's been missing. So certainly this fresh burial on the top schematic, for example, that's fairly obvious where it is. You can see the grave cut. There's no vegetation over it. It's obviously disturbed, so that's a walkover job. As you start to decompose, you let off lighter than air gases, methane, volatile organic compounds, that sort of things. Sort of days to weeks in our temperature and climate in the northern hemisphere. That's where the dogs teams will come in. So late stage decomposition, your chest cavity collapses, the soil around you compacts, new vegetation grows up, Those you sort of look for those sort of signatures, I guess, as well as things like the actual plume, the sort of conductive fluid emanating from the body. And again, it depends on soil type. Of course, it's clay soils, it tends to be retained within the grade cut itself. Sandy soil, it tends to move further away, so that could be a bigger target to look for. So you could maybe use electrical resistivity techniques. And lastly, when the body's been skeletonized, maybe months to years, depending on depth and climate and things like that. That's when you get it's more static, more like an archaeological target, I guess. That's more radar sort of dominates. So you're looking for actually physical objects. You may get some leachate left in the soil, although it's harder to detect. So that, again, it's sort of time frame of burial could be quite important, as hopefully I've emphasised. Other things to worry about, things like depth, as I've mentioned. The deeper the body, generally the longer it will take to skeletonize. So 1/2 metre buried, which is the average discovered clandestine burial depth. Skeletonizing maybe a year, after climate and temperatures. 2 meters down, it may last a lot more. So again, harder to find, but it's there longer. Of course, environment conditions are important as well. So it's very peat bog man, if you've read that, tends to last a lot longer. Or if you're very cold or dry, or both, it tends to be mummified. So like those child Inca sacrifices that we finding in volcanoes in South America that are there from the sort of mid 1500s. If it's really hot, of course, you'll break down a lot faster. So body's left on the surface, especially if you're thinking like the southern US. It's really hot. You can actually decompose in a matter of days. So again, the environment and deposition surrounding the burial or the body is as important as the body itself. Okay, so geophysical basics. There's active and passive methods. So most of them are active. They use some sort of technology, sending some sort of signal around it and into the ground, ideally, and then you measure some sort of response or return. And you're looking for differences as you move the instruments around, and then normally on a survey grid pattern. Passive methods, only two there is gravity, which you probably don't need in a forensic context, and magnetics, which you will. So you're measuring local variations in the Earth's magnetic field. Within each technique, there's sort of different equipment you can use that have different penetration depths, for example, different resolutions, but then there's a knock-on effect with sort of sample spacing as well. So again, it will depend upon what you're looking for, the size of it, the depth of it, and then what you've got available and the environment, as I've briefly alluded to. So ground penetrating radar, that's the most common one. It's an active method. You're pulsing an electromagnetic wave from a transmitter, picking up a response from the receiver, and that's sort of most commonly used ones. We use for high different frequencies, of course, as well, which I'll talk about briefly. So high frequency, you're looking for smaller objects, but you can penetrate as far down. Low frequency, you can see a lot further down, but your resolution is not as good. And it never looks like this, by the way. I've just stolen this off a CSI program, but you don't see a flaming skull. It's not quite that easy. But the nice thing is you can see it in real time. You can get an idea of depth to target and even target size. So people love it. So civil engineers looking for buried pipes, that sort of stuff, it's really commonly used. And forensics is as well. Other sort of slight caveats to that, it's not good in high conductivity soils, saline soils, for example, near the sea, clay-rich soils, which we've got a lot of in the UK, and also these roots and things like that. You get a lot of non-target responses as well. So you've got different set frequencies, normally in the megahertz range. Sort of low frequency would be something like 50 to 100 megahertz, and high frequency maybe up to 1200 megahertz or 1.2 gigahertz. And you basically move it along a survey line. You're getting a vertical slice of the ground. As you sequentially move it along, you're collecting a series of 1D traces to create a 2D image, such as shown at the bottom here. So rather than seeing a skull, you'll see this sort of half moon shape, because as you're right over it, it's the shortest time for the wave to go down and bounce up again off the item of interest, and as you go further away, it takes longer for the wave to go down and up again. So that's where you get that sort of half moon shape or half hyperbolic reflection event is the POS word. So you can see on the bottom is an example of typical data. So you've got a 2D slice, a distance along the top, depth down the side. It's two-way time, but you convert it to depth. So anything flat and straight is boring. See the ground air wave, that big bold black line. You've got a big change in soil stratigraphy here, from sandy soil at the top half to the sort of clay below 1 metre. If you see the scale there, that's why it gets a bit confused, reflectors. But hopefully you can see two clear isolated objects within that top sandy unit, so that sort of half moon shape. It's not as clear as just seeing one, because you get the wave bounces between the ground air interface and the objects, which is where you get sort of duplicates or further down. But you certainly can see there's two reasonable sized objects there. That's sort of how big the sort of half moon shape determines will give you a rough idea of how big the target is as well. If that's useful to know. And if you have time, you can collect a lot of 2D lines and then create a sort of 3D grid of data, such as shown here. And that's quite useful, if assuming it's not a massive search area, because it will take you ages to collect. You can actually slice it in different orientations. That cube, they call it time slices because it's actually in time, not depth. You can see on the image on the right, this is in a rural area, so there's a ploughed field. That's why there's red horizontal marks on that top slice. And as you can see through the time slice, as you go down into it, you can see there's sort of a round circular feature on the right hand side, which is, I think, was what the target was. That's an archaeological Bronze Age ring mound, I think, was what they were looking for. So you can see with more information, more time on site, you can get a lot more data, and when you process it, you can get much more information. And a good example of this being used in a forensic context is the Fred West case. Him and his wife, landlords in this house in Gloucester, tended to go through a lot of female rentees. He was busy bumping them off and burying them in the walls and the floor of his house and surrounding area. In the garden, I think they found a few as well. I think neighbours complained of the smell, and this is an early use of radar. You can see a bottom left example of it, a little bit old school now, but it's certainly collecting data and detecting where the bodies were. That's sort of a good example, if you call it good, of how radar was used to find people. It's not all buried, as I mentioned, so a lot of people get buried, or objects get buried in structures. So this is a colleague in Belfast looking for some pipe bombs and detonators that a particular person had cleverly concealed in his house, specifically in his kitchen, I think, behind these tiles. And you can see there's a relatively small antenna transmitter radar instrument in C there, and they're whizzing along the side here looking for where objects of interest are. And there's a little radar slice at the bottom there. You can just about see that half moon shapes where there's pipe bombs and detonators. And you're collecting a lot of data at the high, relatively small grid size there. You can get relatively good resolution. So then you can see which bits you need to take off the tiles, I guess, to find where that was. So you can read more about that in Hollister's paper. This is a site on campus, actually. I did a little work a couple of years ago now, where we're looking for putting someone under a patio. That's quite a common scenario, so don't do that, by the way. So actually put a pig, not a person, under the patio, and then surveyed it over time in a dense grid to start with. And now I've got lazy, and I'm just doing it once a year with a 2D profile. By using different frequencies here, so you can see the scenario on the top left, then the bottom left is some data, just a 2D slice of low, medium, and high frequency radar slices. You can see the little white arrows is where they might be. And it looks like, rather than seeing a half moon shape, you see more of a sunken depression, which is probably what's called, I've tried to draw on the bottom right, this sort of where the soil starts to compact, and you're actually picking up the air gap probably rather than actually the pig itself. So that's quite useful through time, trying to do this sort of repeat simulated studies to get an idea of what the data would look like if you're looking for someone under a patio. This is a good example of a no-body murder. So this is where the police had approached Alistair Ruffle in Northern Ireland, looking for an abduction and murder victim. They'd noticed in an area, in an unmarked area in a local church graveyard, there was a suspicious feature, which they then collected a 2D radar profile over. You can see it here, sort of distance along the top, depth down the side. No obvious half moon shape here, just these sort of high high amplitude reflection events in the middle, which slightly overinterpreted, I think, but you can get the idea that there's nothing actually in there. So the police didn't have to dig that down and find it, and actually they found the body some distance away. So it sort of saved police valuable time and resources. So radar, it's relatively quick. You can see it in real time. You can see near surface buried objects, obviously the depth and size of it roughly. Works really well over flat areas, concrete and tarmac, which maybe resistivity can't do, and works really well in sandy soils. However, it is you can't do whole, depending on your spacing of your lines, you can't do massive areas. It's normally a secondary phase technique. Can take a lot of time to process. You've got a lot of data you've collected, and ideally sort of a golf course flat short grass is great. So where it's highly rugged upland areas, maybe trees vegetated, you're picking all the tree roots up, or you're in coastal areas, or you're the ground's full of other non-target objects. It's going to be quite problematic to try and identify where your targets might be located. So conductivity then is an active method. It's pulsing out a signal from a transmitter, TX on this diagram on the top right, and then recording both the remnant primary fields that you've transmitted and any secondary fields that gets generated by the receiver, the RX on the image. It's really good for things looking at things like disturbed versus undisturbed soil in certain environments. So quite a useful method. Different systems as well, from relatively large airborne helicopter surveys, such as you've seen here. Presumably the transmitter's under the helicopters. You're not picking up the helicopter as a target, but of course you will be because it's conductive and metal. Down to sort of smaller spaced transmitter receiver pairs, ground based, such as the middle version, down to sort of much more smaller scale, such as the one on the right. So again, depending upon your sample spacing or your target size, will depend upon what sort of configuration of equipment you'll want to be using. And normally you'll collect data in a grid pattern, such as shown on the right hand image, and then building up sort of a digital surface of that location. So metal detectors are actually EM fields. Their transmitter and receiver cores are really closely spaced together, such as you can see on the sort of image on the right. That comes down to sort of lack of penetration depth, because the closer you put them together, the less bulk area that you sample. So you're only seeing maybe half a metre to a metre with a metal detector. But it can be quite useful, although you're going to pick up lots of anything that's conductive, not always just metal, other things as well. The more advanced metal detectors, you can pick up different types of metal. That's actually the sort of hunter detective type things. My colleague Lawrence on the left here is in a specified survey area by the tape, and is trying to use that metal detector in that method. And ideally, you're collecting your data in a very systematic fashion, so you're not missing any areas, moving forward in a specified area, picking up things, and then maybe having flags to mark where conductive objects are located for your sort of digging teams to come up and confirm that. And this example on the right from a job in Wrexham I did a few years ago, unfortunately they'd come before we did the geophysics. You can see there's quite a few water fields, separate areas where they've dug up whatever it was. So of course, using another method such as resistivity will pick up those water filled holes rather than what we're looking for. So there isn't meant to be a sort of stages of investigation you should be doing, not in that case. And a classic case of using conductivity to find missing person is Nobes 2000 study. She's trying to find Yvonne, been missing for 12 years, and they'd actually sort of contained it down to a relatively small area in woods, 60 by 50 odd in that diagram there. Helpfully in grayscale, I'm afraid, but high conductivity is white and low is black. You can see there's some bullseyes of those different colours. He then, I think he did a second phase of radar over each of those to confirm if there's anything there or not. And she was actually found in that sort of circled area ring at the top. So that's a good case study to use. We've actually used this ourselves on a missing person case from the 1970s, not too far from Kiel, on Cannock Chase. There's a specific area that a witness was taken to by their boyfriend and said they'd bury someone there. I don't know why you do that, but there you go. This is the area that the police team had asked us to search. So again, it was fairly remote, rugged terrain. It's got sort of mature deciduous woodlands. Not that easy to see what might be there. They'd also had some evidence suggest that they'd actually been buried vertically, which is much more unusual. Most people tend to get buried horizontally because it's harder to dig, obviously, a vertical hole. But that also means you're going to have to tighten up your grid spacing because it's got a smaller target on top, as you can see by that schematic. Did a little brief desk study, not much happening from the information we had. You can see a little red dashed area there from the woodland that's growing. I had a little look on site, so a reconnaissance survey. Did find this bolt, which is interesting, but then did a bit of analysis, or Duncan Peary at Swansea did some analysis for us, and thought it was a pin for a trailer. So they thought, maybe they were bringing the body in on the trailer and then dumping it, but it could be due to something else, so we just don't know. We then did the surveys, did a variety of collectors, did metal detectors first, looked for things, such as that bolt. Resistivity, it was too dry, too thick leaf mulch for that to work. The resistivity values are too high. Did a conductivity survey as well. This is what this is showing. We actually used a small mini explorer, which actually has 6 cores in it, so you can collect 3 different depths effectively with the different spacings. As you can see here. Obviously, there's a big, larger site trend of high at the bottom to low towards the top, as you can see there. Not too many things to discriminate. There's maybe a few on the edge effects and things like that. We also had to go with some magnetics, radiometer, I think. There was a few targets in there. We also did some radar as well. So we combined all that data to the plot on the right-hand side there, and where they overlapped, that little sort of black square in the bottom. We actually did some digging, but it was a large tree root and a significant sized rock, so wasn't actually there. Wasn't actually found there. So then we could say to the police, well, we've used all the equipment at our disposal and didn't manage to find anything at that location. You could read more about that in Chris's paper. This is the in phase, I think, so remnant primary field, which shows you a lot more information. So you have got a few related isolated targets there compared to the others. So connectivity then, you can carry it, so it's relatively quick. You can rapidly survey areas, much quicker than radar, so it's quite good as a first pass technique, certainly within rural areas or areas that are relatively homogeneous. That's quite useful. So certainly use it in the woods, for example, and over concrete, and you can't with resistivity. However, you do get some one value, which could be a variety of things causing that thing. You can get above ground interference with anything metallic, for example, including the operator if they're collecting data as well. Doesn't tend to work too well in clay soils either. So resistivity then, that's the inverse of conductivity, how resistant something is rather than how conductive it is. Used loads right back to the 1800s for hydrocarbon exploration. And generally you're using a 4-probe sort of configuration, so 2 potential probes and 2 current probes. The potential one's measuring the voltage, and there's different ways of moving those around. And generally, the wider the spacing the probes, the deeper you see. But then, of course, that means your resolution goes down as well. And you get it some sort of system, so a twin pole, such as this example, where you have a reference probes and the mobile probes moving along a specified survey grid is sort of the usual way of collecting. Here's an example in Arkansas, looking in a graveyard. So the known graves are the grey rectangles on the top right image. They're collecting resistivity data. You can see that in the top left equipment, and then the results on the bottom right. So you can see some relatively low resistance rectangles, which correspond to some of those known burials, but also there's some others that aren't on that known graveyard plot. So it can be quite useful method. Of course, there's complications with how large the graves are, how long they've been there for, that sort of things, which maybe why they're quite different anomalies being located. And certainly looking at resistivity, there's been quite a bit of work on that using controlled sites, say sort of pretend graves. So they often use so Patricia Cornwall, before she was a famous author, she was actually a police sort of investigator, and they used a variety of controlled experiments, dispatching bit grisly pigs in different ways and then trying to find them again. So that's certainly something that we've tried, but not dispatching them obviously. At Kiel, and also other researchers worldwide have been doing sort of control experiments to try and help police find what methods might work well and what ones won't, depending on the situation involved. And certainly pigs are quite useful for that. We can't use humans, unlike in the US and Europe actually, and Canada and Australia, which are the other sort of body farms that they have around sort of those sort of human taphonomic facilities. Due to the Human Tissue Act. You can use resin skeletons. We've done that as well. If you want to read more about that, read that article. Or you tend to use sort of animal carcasses. They're quite good for things looking at time since death, where burials might be located, and by repeatedly monitoring them over time, you see which methods work best and does that change. And you can argue pigs work better than humans as analogues for that, because they're known size and weight. They've got similar tissue styles, skin and hair types, organ sizes. We know how they decompose. And you can get replicants if you're doing quite a few studies or trying to make sure it's statistically significant. They're actually better than human donations because you can get them the same, as I mentioned, same size or weight and things like that. So just it's a famous 60s time-lapse plot of decomposition of a pig, so you can get the idea of how they decompose over time. And this is that's Staffordshire University's crime scene house. They've got a wall, sort of not wall, a garden out the back, which we've buried things in historically. So here there's a couple of pig carcasses we've buried. You can actually see, they're highlighted here on the plot, but actually the grass looks a bit green if you notice. It's not a good pointer when you're looking for things. Anyway, so here we set up a survey grid. You can see there on the image, and then a series of grid lines which you then collect sequentially over it to record the values, and then create a digital surface to connect those values. And you can repeatedly do this over time to see what changes there might be. You can also do things with these lightometers, which are like vertical tubes stuck into the ground, measuring soil water, or if you put it next to another big, you can actually take out the fluid and then measure its resistivity or conductivity and relate that to your results as well, which is quite nice to calibrate stuff too. So here, for example, is some repeat data I've taken over several months. There's a big block of concrete, I think, which is what that big red high resistivity thing is, on the top right of each of these plots. And there's also a pipe going along the top, so that blue linear line is. But the actual pig itself is in the middle. I think it's been disemboweled, unfortunately, so that's why it's two separate low anomalies in the middle rather than a whole one. But you can see its location repeatedly over time, and it actually changes over time as well. So that's also interesting to see what time of year is best to collect data from, which does seem to vary as well. It tends to be winter, actually. It tends to be better. Get less non-target anomalies, interestingly. We used resistivity in this case study. We asked to locate a suspected murder victim being shallowly buried in a rural area. She'd been missing about a year. I think she'd gone missing the day before her lover's family from Poland had come over. And the police had bugged the suspect's car, and he kept driving around these rural fields south of Wrexham. This is where they got us involved. So we had a little look at some of these sites. They'd done the search dog teams, metal detector teams, but the forensic geomorphology teams didn't have any success finding where she might be. So we had a look there. The soil was really clay rich, so the radar wasn't going to be working too well. Very wet as well, so we thought resistivity might do well. So we looked at the first field specified, had a little look at it, and decided to do some surveying. We then looked at our resistivity data from our pigs that had been buried for about a year as well, to see what they would actually look like. So we collected a lot of survey grids. So for 3 long days in the field, collecting sort of on a grid system. Subsequently processed that data. So here's an example of one of the data sets. We've actually normalized it as well to try and get make it more consistent, basically, to try and to merge the different grids. And then we actually use GMT, sort of free software, to actually automatically identify any anomalous points. You can probably see a sort of a really low resistance in the sort of bottom left plot, looking suspiciously grey. So, and actually the software actually automatically looks at them for the same sort of size that we specified, of a grave size, and also the signal strength of it as well. So the priority ones are the ones in red, the numbers. Other ones tend to be bigger than that, maybe non-targeted to other things like different soil moisture perhaps. You've got grid edge effects around the grids, that side of things. Once you merge everything, some of those grid edge effects go away because you're obviously merging different grids, but certainly on the edges of the grids you're still having those factors as well. So that's so the specified area was in this entrance gate in the middle of this plot, and we were told to go 200 meters either side and 10 or 20 meters in. It's based on average statistics, I think. Within that data, you can see there's obviously some big red blobs of high resistance values, which are going to be too big for someone being present. But certainly the areas which are of interest, we've actually highlighted those red numbers of different sizes. You can see there's not loads in there. We really picked 7 areas that looked of interest for the police to go and do some more digging, or other search teams to do digging. Other things, as I say, maybe due to other things, soil moisture or grids, things like that. In the end, actually, he was actually watching us collecting it, and the police were watching him. And he then tried to move her remains the next night after we left the site, which is in the next field, not the field we collected data in. So we would have picked her up though, because she was only found 18 inches down in the field. You can see there's a plot of her there, I think, with the arm up on that left diagram. So he was actually not only arrested and convicted of her murder, but also with the illegal deposition of her body. Yes, that's if you didn't know, you also get preventing a lawful burial is another crime. There was some suggestion to suggest you may be in a suitcase or wrapped. We weren't sure, but because he'd bought a suitcase recently after she disappeared, but she wasn't in that, and he was sentenced to life in prison. Okay, so resistivity, you can change the spacing of the probes to have different depths if you wanted to. You can sort of, it's quite repeatable if you get similar values each time you put it in the same spots, and it's less affected by above ground source of interference and light conductivity. However, you've got things to worry about. You can't see too far down. It's sort of spacing issue. So small objects deeply buried, it's going to be tricky with resistivity. Soil moisture is a big problem, especially in the summer or when the soil is dry. So the wetter winter surveys tend to work better looking at the control data. And of course, you're going to put the probes into the ground, aren't you? So you're getting a little bit of surface destruction. Magnetometry, that's probably one of the other big things that we use. It's a passive method, one of the most commonly used actually, more for geotechnical or environmental uses, and you can use it land, air, or at sea, and you're measuring basically the subtle variations in the Earth's magnetic field due to whatever is near your instrument. So obviously got issues above and below ground. It's relatively quick to collect, relatively easy to maintain the equipment. Not many corrections to do depending on what you're collecting. Of course, it's going to be a variety of things could be causing it. So it could be one big thing or lots of little things that give you the sort of similar results. That non-unique issue is tricky. And can collect a lot of. In fact, you can have non-magnetic things. So this example from RSK Stats Limited, they're looking for buried air raid shelters. They're actually picking up relatively low magnetic anomalies. You can see the subsequent excavation diagram underneath the data. So you can see at the top of each of these, there's sort of 4 air raid shelters, I think, which actually come up as relatively low blue magnetic anomalies compared to the background higher green and red areas. No key, hopefully. So we've had a little go at this a few years ago, looking at buried weapons, for example, which should get picked up magnetically. So there's a variety of things we've buried here. You can see that there on a specified survey area, which we then surveyed once we've buried them. And then we then put a patio on top and then surveyed them again to see what effect that might have. And no surprise, it's harder to find under the patio versus not. Susceptibility is also magnetic survey. And you can see here, it actually picks up most things really well. And also something weird on the bottom left, which I hadn't actually buried. So not sure what that was. It's definitely, and if you also notice is that you get a characteristic dipole anomaly. You get a high and a corresponding low. So number 10, for example, the ammunition box, it quite nicely delineates where those two are. It's usually between the high and the low. So you're not always looking for high values. You're often looking for this sort of dipole signature, so in between the two, which gives you a good number 11 as well, the mortar shell. It's a nice example of that. The radar works reasonably well. You're picking up the ammunition box, for example, but it's not all of them. You can detect which is the target and which isn't. So certainly in an urban area, back gardens or whatever, it's going to be quite tricky to work out where things might be. This is interesting as well, looking at susceptibility. So this is a grave found in East Anglia, I think RAF Lakenheath. They've dug up the anomaly after they've done the survey. So you can see that's the middle diagram here. We've superimposed the skeleton onto the data on the left-hand side. So you can actually get quite a high values around the grave versus relatively lower values around it, although there's not actually any metal in there. So that's interesting. Not sure why that might be. Is it some sort of bacterial action, sort of eating up the blood and the bones and leaving some signal behind? Is it some sort of disturbance issue or something else? I'm not sure, but certainly that works quite well. So even if there aren't any magnetic targets to be found, it may still be worth collecting because you're still seeing an anomaly in that example. So magnetics then, relatively quick to collect. I haven't shown you too much kit, quite flexible, but a variety of things could be causing it. If you're measuring total field, you'll need to worry about it varying over the days. You need to do some sort of base station repeat data collection to correct for that. And of course, if you've got a busy, small urban area, you can have a lot of other targets that might be interfering with your data. So again, depending on what the site's like, will depend on which method you might want to use. Okay, it's not all about land as well. I mentioned talking about water burials. A lot of people get dumped in water or drown, of course. unfortunately. So how are they? How do you find them in a large area? So sort of lakes, ponds, and the sea. Of course, you can use some sort of sonar system, so sort of acoustic sound waves measuring a response. So you're getting a sort of a response image rather than like a photographic image, for example. So use some sort of machinery. You can see here either some sort of boat, or this one's from Schultz's paper, looking at a relatively smaller boat, and you're towing some instrument behind. Obviously GPSing where you are, so you know where you can put the data in a location, and then gridding up some sort of data, some sort of graph. So here's some examples. So they are images, but they're reflective sound wave strengths. You can see where the towfish was, the instrument, by the linear line on the left-hand diagram, and then you can see fairly obviously a sunken boat on that sort of on the lake seabed on this example. On the right-hand side, I think this one's from New Jersey. Someone's been weighted down, concrete boots is that the term, weighted down and pushed off the edge of the harbour and drowned, obviously. And you can see there, the zoomed in image of a head, body, and legs there. So that's quite useful, assuming your target is relatively bigger than a substrate. So you imagine with the body in the harbour, that's relatively easy to see. But if that's very rocky on the bottom, you'd have difficulty locating where the body might be relative to the rock. So certainly your targets will be bigger than the substrate. So that's one of the issues with these sort of surveys. This one's actually in one of Alistair's review papers, testing different bits of equipment. So I think this was a drugs bust of a canal boat. And I think they'd panicked and tried to dump stuff off the side. And so police were then asking Alistair, or approached him to say, well, which methods would have found those drugs in the water? So they went back to that site, collected some water penetrating radar, which is basically a radar system in a boat. You can see that on the top right image. And then it still collects data as you can see here, but rather than the ground interface at the top, that's a surface. Then you can see where there was water canal bed surfaces, that's all relatively rugged terrain halfway down the plot. You can see some sort of some floating objects in there. It's sort of linked up, or things. It's more hard to tell where it is in the canal bed, but of course radar actually penetrates below the actual surface, the sediment. Water interface. You can see some buried stuff which sonar wouldn't pick it up, so that's why water radar is actually quite useful. If you actually look at the sonar data, you can see there's this sort of side of the canal bait. There's some, and they've tried to differentiate between the surface targets on sonar, stuff that's in sediment which you won't see on sonar, and then other stuff as well. So you can see it's quite useful. So if you're a police dive team, you've got areas that you want to go and actually have a look at, and again you can prioritise those on the ones that you want to dive for first. So that's certainly moved away from gridding bottoms of lakes and ponds and working your way through, which would be pretty slow and painful for the dive teams, I would think. Other stuff as well. There is water-based LiDAR these days. So again, this is a plot here of some well, you can see the London Bridge on the left, and there's another canal on the right. So again, that's quite a useful method to locate where things might be on the bottom of the water surfaces. And again, there's a YouTube link there for you to have a look at. So for simple graves, maybe conventional methods might work best, or other things you're looking for. Certainly where things are older, or you're a bit more unsure, then maybe geophysics would work. And you may be picking up the disturbed ground rather than the target itself. You may be picking up other non-target objects as well, which you need to try and differentiate. And of course, different things might work best differently. So Kenneth Pye's little summary plot there on the top right gives you some sort of metal detectors, magnetics, EM, and radar. Hasn't got resistivity in there actually. And then looking at some sort of common things to look for. You'll often see those sort of plots of which applications might work best. So resistivity, useful. Certainly different methods with that. Radar is really good. Connectivity could be good as reconnaissance surveys, as I've shown you. So I've shown you some different examples. You've got an idea of the techniques, and shown you some relatively case studies. But certainly need to do a bit more work on this to make this a mainstream activity. So you want to read more about that? There's a field geophysics little textbook. That's quite good actually for a little guide. So how each of the techniques work. The geoforensics Ruffler McKinley book is really good. Shows some examples of case studies. And if you want a sort of more coffee table type book, Ray Murray's Evidence on the Earth book is quite useful. I've also referenced obviously all these ones I've just talked about now if you want to read about more detail.